Today is week 3, part 3 of our physics lectures, and I wanted to go back to one of the problems. You recognize this slide from the last part, and I was talking about how you would go about finding VA and VB, and I made a mistake in the calculation, and I wanted to correct that. And where I made my mistake is right here. Here I said that the angle that would be used for B is 26.5, and that is actually not correct. If you look here, it's clear that the angle here is greater than 26.5 degrees, and in fact, the way you find that is here's a line that is intersecting two parallel lines. If you have a line here that represents the x-axis transposed to where the head of VA is, and when a line intersects two parallel lines, then these two angles, this one and this one, have to add up to equal 90 degrees. And so indeed, the angle for this second one is 67.5, or 90 minus 22, as opposed to the 26.5 that I put in here. And in this part, I've done the rest of this calculation and how you would go about finding this answer. And eventually you have two equations. You have this equation for one, and you have this equation for the other. So you have two equations and two unknowns. You then solve one of the two equations for one of the variables, and then substitute that solution in the other equation, and then work out the mathematics. And so that is a correction of that. So I wanted to go on now and talk about the next topic, which is projectile motion. And projectile motion is the two-dimensional equivalent of a free-falling object. That is, it's an object that only has gravity acting on it, but we're looking at its path in two dimensions now, as opposed to a single dimension on the y-axis. And what you can see here is the path of the object is different than its displacement, which is no surprise. And again, finding this displacement is very similar to what we've already done in the past, looking at the x and the y components of that situation. So one of the very important principles that must be understood is shown in this slide. And in order to analyze the projectile or two-dimensional motion of an object, you have to start out by understanding or breaking that motion into two independent one-dimensional components: the vertical component and the horizontal component. The horizontal component turns out to be the simplest part because there's no force acting on the horizontal component, therefore there's no acceleration, and Vx, the x component of any velocity, remains constant throughout its flight. And you can take advantage of that. The y component, the vertical component, has gravity acting on it throughout its entire flight, and so as it goes up, it decreases in velocity until it reaches the peak or apex. At that point, the y component of the velocity becomes 0, and then it falls, again with gravity being the only factor that's affecting it, and the y component of velocity is the same here as it is here. And therefore, beyond that, the y component becomes bigger and bigger. Now, very important to remember, is that these two are independent of each other, and also very important to remember that these act together to form the velocity component, the combined velocity component at each point. Let's now take a look at an example of how to do a problem with these principles in mind. And here we have a situation where a firework is fired off and it's set to explode at its highest point, which is found to be at a height of 233 meters, 125 meters away horizontally. And the question is, what is V0, both in height or in magnitude, and they already give you the trajectory of 75 degrees, so all you have to do is find the magnitude of this in this problem. So let's take a look at how we would go about it. First of all, remember that V0 is going to equal Vx plus Vy. And also remember that Vx is a constant, okay? It never changes. So, what about Vy? What can we say about Vy? Well, what we know here is when the firework reaches this top point, we know that when the firework reaches here, the Vy is equal to 0. So at the very top, Vy equals 0. So the final velocity, the velocity at the top here, Vyf, if you will, is 0. And we know that Vy initial then is something we need to find. And so we know from our last week that if you take the final velocity squared, that equals the initial velocity squared plus 2 times the acceleration times the distance. In this case, we've got 0 equals Vy initial squared plus 2 times g, which is times the distance, which is 233 meters. And we know that g equals 9.8. And so we can do this math here and find out what Vy initial is. So the answer here for Vy initial equals 67.6 meters per second. Now we also know that Vy initial is equal to V0 times the cosine of 75 degrees. So that means that V0, the magnitude of V0, is going to equal Vy initial divided by the cosine of 75 degrees, which is going to equal I made a mistake here. It's the sine. Vy is the side opposite, so it's the sine. So let's do that again. So that equals 70 meters per second. So that means that V0 is 70 meters per second at an angle of 75. Now we could also calculate some of the other factors here, and you can do that. You can find what Vx initial is, and it stays the same throughout, and you can find the time that it takes to reach the highest point after you find that. Okay, so here's another example. This is a volcano, which I'm not going to try to pronounce. And what it says is that suppose a large rock is ejected from the volcano at 25 meters per second squared at 35 degrees. And it strikes on the other side of the volcano at a point 20 meters below the top of the volcano where it starts. The first question is calculate the time it takes the rock to follow this path. And the second question is what is the magnitude and direction of the rock's velocity at impact? Now, the best way to look at this is to understand that, again, when you reach this apex, your velocity is going to be 0, and it's also half of the time it takes to go from here to here. So you can calculate this much of the time using that fact. Also understand that when it reaches this point, it's headed down exactly the same way it's headed up at this point. And therefore you can calculate the down vector and use your distance here plus that calculation in order to find what it ends up being here. So let's look, and I may not do the entire thing this time. I may let you do some of the calculation, but let's take a look at this. First of all, we know we might as well go ahead and calculate Vx and Vy, which would be the first thing I would calculate anyway. This Vx first thing is going to be 25 times cosine of 35 degrees, and Vy is going to be 25 times the sine of 35 degrees. And I'm going to get this number first because this is the one we're going to need to do most of our calculations. So that equals 20.5 meters per second. Now remember, at this top here, the V is 0, so we can do a calculation very similar to what we did the last time, which is 0 squared is going to equal 20. Actually, we don't need to do that way. What we can do is we can know that D is equal to V0t plus 1/2 GT squared, okay? And we can also use the 0 is equal to 20.5 squared plus 2 times G, or 9.8 times D. We can get D from this equation and put it in here, and with that we can find this. But remember, that's only going to be half of the path. And so let's go ahead and do the calculation to find out what D is. So the path to the top is 21.4 meters. And then we can put that in here, and we have 21.4 meters is equal to 20.5 times T plus 1/2 times 9.8 times T squared. And that I'll let you all do the math here because that would take a lot of time, and I'm not sure I want to take that time. So that'll give you the time to the top. Of course, you'd multiply that by 2 to get to the time to this point. Okay, now how about finding the rest of this? Well, we know the downward vector here, Vy down, is equal to 20.5 meters per second. And we also know that it's free falling with gravity, and it has to travel minus 20 meters. So again, we know that this would be the initial, and the final would be unknown. So we would have Vy final squared is equal to 20.5 squared plus 2 times minus 9.8 times minus 20. And if you do this math, you get a downward vector of approximately 28.5 meters per second. Now the y component never changes, so that we can use this to find the y component. Once we've found the y component, we can then use Pythagoras' theorem to find all of v. And so I'll let you do the rest of the math on this, and if there are questions we can do it in class, but I'm going to leave it at that point for that. I'm going to talk about one more thing before we stop, and that's shown here. when you look at different trajectories, there are different ways to show the effect of various manipulations on the distance that's reached. In other words, if you're trying to decide on the range, there are two ways to affect the range. Here, we're keeping the angle of the projectile force in the same angle, but we're increasing the velocity, and that's one way that you can increase the range down range. The other way you can do that is if you keep the velocity the same but change the angle of projection, it changes the range as well. So there's two ways to affect the range. First of all, we can change the velocity and keep the angle the same, or we can keep the velocity the same and change the angle of projection. There will be one more part that we will go through the final few slides that I have to show you this week.